Welcome! In this session, we'll be exploring the problem number 1824, minimum sideway jumps. We'll break it down step by step, evaluate different approaches, and understand how to solve it effectively. Let's dive in. In this problem, we are tasked with helping a frog navigate a 3-lane road filled with obstacles. The road is represented as an array called obstacles, where each index corresponds to a position on the road. At any given position, the value in the array tells us if there's an obstacle in one of the lanes. If the value is 0, it means there are no obstacles at that position. If the value is 1, 2, or 3, it means there's an obstacle in lane 1, lane 2, or lane 3, respectively. Now, the frog starts in the middle lane, which is lane 2, at the very beginning of the road, position 0. The goal is for the frog to reach the last position of the road, N1, where n is the length of the obstacles array. To do this, the frog can move forward one step at a time, but it can also make side jumps to switch between adjacent lanes. However, the frog cannot jump into a lane that has an obstacle. Our task is to determine the minimum number of side jumps needed for the frog to safely reach the end of the road. The input to the problem is a list of integers called obstacles, which represents the road. The length of this array is n, and each element is a number between 0 and 3. The output is a single integer, which represents the minimum number of side jumps the frog needs to make in order to reach the last position. Let's look at an example to understand this better. In the first example, the input is obstacles equals 0, 1, 2, 3, 0. Here, the frog starts in lane 2 at position 0. At position 1, there's an obstacle in lane 1, so the frog stays in lane 2. At position 2, the obstacle is now in lane 2, so the frog makes a side jump to lane 3. At position 3, there's an obstacle in lane 3, so the frog jumps to lane 1. Finally, the frog reaches position 4 in lane 1, having made a total of 2 side jumps. This is the minimum number of side jumps required for this input. Let's look at another example. For obstacles equals 0, 1, 1, 3, 3, 0, the frog starts in lane 2 at position 0. At positions 1 and 2, lane 1 has obstacles, so the frog stays in lane 2. Then, at positions 3 and 4, lane 3 has obstacles, so the frog continues moving forward in lane 2. By the time the frog reaches position 5, it has not made any side jumps, so the output is 0. In another example, obstacles equals 0, 2, 1, 0, 3, 0, the frog begins in lane 2. At position 1, there's an obstacle in lane 2, so the frog jumps to lane 1. At position 2, lane 1 has an obstacle, so the frog jumps to lane 3. From there, the frog moves forward in lane 3 and reaches the end. This time, the frog made 2 side jumps, which is the minimum for this input. Now, let's consider the constraints and edge cases for this problem. The length of the obstacles array, n, is guaranteed to be at least 2 and can go up to 500,000. Each value in the array is between 0 and 3, and there are no obstacles at the starting or ending positions, meaning obstacles, 0, and obstacles, n1, are always 0. For edge cases, if the array contains only 0s, the frog can move straight to the end without making any side jumps. Another scenario is when obstacles alternate between lanes, which might force the frog to switch lanes frequently. Finally, since the length of the road can be very large, the solution must be optimized to handle up to 500,000 positions efficiently without running into performance issues. To solve the minimum sideway jumps problem, we considered several approaches, each with its own trade-offs. The primary goal is to minimize the number of sideway jumps required to traverse a 3-lane road, which is represented by the obstacles array. One straightforward method is the brute force approach, where we simulate all possible paths from the starting position to the end. At each step, we evaluate the cost of either staying in the current lane or jumping to another lane, and this is done recursively for every possible scenario. While this method is intuitive, it involves exploring all combinations of lane changes, leading to an exponential growth in the number of states. Specifically, the time complexity is 3 to the power of n, where n is the length of the obstacles array, and the space complexity is n, due to the recursive stack. This makes it impractical for large inputs, as the number of calculations becomes overwhelming. Consequently, while brute force provides a baseline for understanding the problem, it is not efficient for competitive programming or large datasets. A more efficient approach is to use dynamic programming, which leverages the optimal substructure of the problem to minimize redundant calculations. Here, the key insight is that at each position, the minimum jumps required to reach the end can be computed based on the current lane and the presence of obstacles. Importantly, the frog only moves forward or sideways, significantly simplifying the possible state transitions. The obstacles array plays a crucial role, as it tells us which lanes are blocked at each position. This problem is well suited to dynamic programming because it has overlapping subproblems and a clear optimal substructure. To implement this, we define dp, I, j, as the minimum number of sideway jumps needed to reach the end from position I while in lane j. The base case is straightforward. At the last position, no jumps are needed in lanes without obstacles, so dp, n1, j, equals 0. The transitions involve two possibilities, either staying in the current lane, if it's clear, or jumping to another lane, if the target lane is not blocked. Finally, the result is the minimum value of dp, 0, 1, dp, 0, 2, and dp, 0, 3, since the frog starts in lane 2. This method systematically breaks the problem into smaller, manageable pieces while ensuring efficiency. The dynamic programming approach has a time complexity of O(3*n), which simplifies to O(n), as we calculate the state for each of the three lanes at every position. The space complexity is O(3*n) to store the dp table, but this can be optimized to O(3) by maintaining only the current and next states, significantly reducing memory usage. This optimized space version trades some readability for memory efficiency but is still practical with careful indexing. Ultimately, we chose the dynamic programming approach because it strikes the right balance between clarity and performance. Unlike the brute force method, it avoids redundant calculations and scales effectively for large inputs, even up to n equals 10 to the power of 5. The optimized space variant further enhances its suitability for environments with memory constraints. While dynamic programming is more complex to implement than brute force, it is significantly faster and more practical, especially in competitive programming scenarios. It also handles challenging edge cases, such as consecutive obstacles, in a structured and reliable manner. Overall, this approach leverages the problem's constraints and observations to deliver a robust and scalable solution. The minimum sideway jumps problem is all about navigating a three-lane road with obstacles while minimizing the number of sideway jumps. The road is represented by an array called obstacles, where each position indicates whether or not there's an obstacle in a specific lane. For instance, if obstacles I equals 0, it means that position I is clear for all lanes. On the other hand, if obstacles I equals k, there's an obstacle in lane k at that position. The goal is to start in lane 2 at position 0 and reach the end of the road with the fewest sideway jumps. To solve this, we use dynamic programming. First, we define the state dp, I, j, as the minimum number of sideway jumps needed to get to position I while staying in lane j. At the start, we know that dp, 0, 2, is 0 since we begin in lane 2, while the values for lanes 1 and 3 are set to infinity because starting in those lanes is not allowed. Next, for moving forward, if a lane at position I is clear, meaning there's no obstacle in that lane, we can continue moving forward without any sideway jumps. This is captured in the equation dp, I plus 1, j, equals dp, I, j, for such cases. Now, when it comes to sideway jumps, we need to consider switching lanes to avoid obstacles. From lane j at position I, we evaluate the other two lanes, say k, to see if they are clear. If there's no obstacle in lane k, we can update the value of dp, I, k, to account for the sideway jump. Specifically, this is done using the formula dp, I, k, equals min, dp, I, k, dp, I, j, plus 1. This ensures that we're considering the minimum number of jumps required to transition lanes. The process involves iterating through all positions along the road, from the start to the end, and performing the necessary updates based on whether we're moving forward in the same lane or jumping to a different lane. Additionally, if a lane at position I is blocked, meaning obstacles, I equals j, we set dp, I, j, to infinity to indicate that it's not possible to use that lane. Finally, after populating the entire dp table, the result is obtained by finding the minimum value among the three lanes at the last position. This gives us the least number of sideway jumps needed to reach the end of the road. There are some important insights to keep in mind for this problem. First, relying on a greedy approach, such as always moving forward in the lane with no immediate obstacle, doesn't guarantee the optimal solution. This is because it may overlook scenarios where making an early sideway jump could lead to fewer total jumps overall. Dynamic programming, however, ensures optimality by evaluating all possible lane configurations at each position. It systematically accounts for every valid path and transition, guaranteeing that the solution is the best achievable. Another critical point is obstacle awareness. By setting dp, I, j, to infinity for lanes with obstacles, the algorithm effectively excludes invalid moves. This prevents us from considering paths that are impossible due to blocked lanes. The main data structures involved are the dp table, which stores the minimum sideway jumps for each position in lane, and the input obstacles array, which is used to check lane availability. In terms of efficiency, the time complexity is O(n), where n is the length of the obstacles array. This is because we only process 3 lanes per position. For space, the dp table requires O(n*3) space, though it can be optimized to O(3) by only retaining the current in previous rows. When solving this problem, it's important to handle certain edge cases. For example, if that obstacles array contains only zeros, there are no obstacles on the road, so the answer is simply 0 because no sideway jumps are needed. Another edge case involves continuous obstacles in a lane. The algorithm accounts for this by excluding blocked lanes from consideration, ensuring that it finds an alternative path if one exists. Additionally, since the problem guarantees that the start and end positions have no obstacles, i.e., obstacles 0 and obstacles n1 are always 0, no special handling is required for these positions. Now, let's summarize the solution with pseudocode. We begin by initializing a dp table with infinity for all entries, except for dp 02, which is set to 0 because we start in lane 2. As we iterate through the road, we handle forward movements in clear lanes and evaluate sideway jumps for transitions to other lanes. At the end, the result is the minimum value across the last position in all 3 lanes. This approach ensures that we solve the problem efficiently while handling all edge cases appropriately. The code solves the minimum sideway jumps problem using a dynamic programming approach. The key idea is to maintain an array dp where dp, I, represents the minimum jumps required to reach lane I+1 at the current position. Initially, the dp array is set to 1, 0, 1, because we start in lane 2, 0 based index 1, with 0 jumps, and the other lanes require one side jump to reach them. We iterate through the positions in the obstacles array, and for each position, we calculate the minimum jumps required to reach each lane in the next position. A temporary array next_dp is used to store these values, initialized with infinity to represent an unreachable state. For each lane, if it is obstacle-free at the current position, its jump count is carried forward to the next position. Then, we check all other lanes and update the minimum jump count to the current lane, considering the possibility of a side jump from those lanes. Finally, at the end of the iteration, the minimum value in the dp array gives the result, as it represents the minimum jumps required to reach the last position in any lane. This approach ensures that the solution is optimized and handles all edge cases, including scenarios with consecutive obstacles or a clear path without obstacles. The time complexity is O(n), where n is the length of the obstacles array, and the space complexity is O(1), due to the constant size of the dp array. Here, we start by defining the method minSideJumps, which takes an array of obstacles as input. The length of this array is stored in n, and we initialize a dp array to keep track of the minimum number of sideway jumps needed to reach each lane at the starting position. Initially, the frog starts in the middle lane, so the dp array is set to 1, 0, 1, where 0 represents the lane the frog is currently in, and 1 represents the side jumps required to reach the other 2 lanes. Next, we iterate through each position in the obstacles array using a for loop. At each step, we initialize a nextDP array to store the updated minimum jumps for the next position. The values in nextDP are initially set to integer.max_value to represent that these positions have not been calculated yet. The first inner loop checks if there's no obstacle in the current lane at this position. If it's clear, the current lane's jump count is carried forward to nextDP. This ensures that if the frog stays in the same lane, the number of jumps remains unchanged. Then, the second inner loop handles sideway jumps. For each lane, we check all other lanes to see if a sideway jump is possible, updating next DP with the minimum value between its current value and the jumps required to switch from another lane plus one additional jump. This approach ensures that we calculate the optimal number of jumps efficiently. After processing all lanes for the current position, we update DP to point to next DP, effectively moving to the next state in the iteration. This allows us to calculate the minimum jumps for subsequent positions based on the updated values. Finally, after completing the loop, we return the minimum value from the DP array. This represents the minimum number of sideway jumps required to reach the final position, regardless of which lane the frog ends in. The use of dynamic programming here ensures that we calculate the result in an optimized way by systematically building on previously computed values. By carefully considering both staying in the same lane and switching lanes, this implementation guarantees the minimum total jumps are determined efficiently. In this example, we start with the obstacles array 0, 1, 2, 3, 0, which has a length of 5. Our goal is to determine the minimum sideways jumps needed to reach the end of the track. The dynamic programming array, or DP, is initialized as 1, 0, 1. This represents the minimum jumps required to reach each lane at position 0. Lane 1 requires 1 jump, lane 2 requires no jumps, and lane 3 requires 1 jump. At position 1, we encounter an obstacle in lane 1. We initialize next_DP with infinity for all lanes, representing that no values are carried forward yet. For obstacle-free lanes, we carry forward the values from DP. Lane 2 retains its value of 0, and lane 3 retains its value of 1. Then, we calculate sideways jumps. From lane 2 to lane 3, the cost remains 1, and from lane 3 to lane 2, the cost is updated to 0. After updating, DP becomes infinity, 0, 1. At position 2, there is an obstacle in lane 2. Again, next_DP is initialized as infinity, infinity, infinity. For obstacle-free lanes, we carry forward the values. Lane 1 retains the value infinity, and lane 3 retains the value 1. Now, we calculate sideways jumps. From lane 3 to lane 1, the cost becomes 2. After this step, DP is updated to 2, infinity, 1. At position 3, the obstacle is in lane 3. For the obstacle-free lanes, we carry forward the values. Lane 1 retains the value 2, and lane 2 retains the value infinity. Next, we calculate sideways jumps. From lane 1 to lane 2, the cost becomes 3. After updating, DP is 2, 3, infinity. At position 4, there are no obstacles, so we calculate next_DP for all lanes. Starting with carry forward values, lane 1 retains the value 2, lane 2 retains the value 3, and lane 3 retains infinity. Now, we calculate sideways jumps. From lane 1 to lane 3, the cost becomes 3, and from lane 2 to lane 3, the cost also becomes 3. This gives us a final DP of 2, 3, 3. To determine the minimum sideways jumps required to reach the end, we take the minimum value from DP, which is 2. In this example, the obstacles array is 0, 0, 0, 0, 0, meaning there are no obstacles throughout the track. The DP array is initialized as 1, 0, 1, representing the jumps required to reach each lane at position 0. Since there are no obstacles, we simply carry forward the values for all lanes at each position. The DP array remains 1, 0, 1 throughout the track. At the end of the track, the minimum value of DP is 0, indicating that no sideways jumps are needed to reach the finish line. In this example, the obstacles array is 0, 2, 1, 0, 3. The DP array is initialized as 1, 0, 1. At position 1, there is an obstacle in lane 2. For the obstacle-free lanes, lane 1 retains the value 1, and lane 3 also retains 1. For sideways jumps, we check lane 3 to lane 1, but the value remains unchanged at 1. After this step, DP becomes 1, infinity, 1. At position 2, there is an obstacle in lane 1. For obstacle-free lanes, lane 2 retains infinity, and lane 3 retains 1. The DP array is updated to infinity, infinity, 1. At position 4, there is an obstacle in lane 3. We update DP based on the carry-forward values and any necessary sideways jumps. After computing these values, we determine the updated DP array. Finally, to find the minimum sideways jumps needed to reach the end of the track, we take the smallest value in the DP array. This gives us the result for this example. Here, we analyze the time complexity of the solution. First, the outer loop iterates through the entire track, which has a length of n. This contributes an O(n) term, as the loop runs once for each position on the track. Next, within each iteration of the outer loop, there are two nested loops. The first inner loop iterates over the three lanes, lane 0, lane 1, and lane 2, to carry forward the minimum jumps for lanes that are obstacle-free. This loop involves 3 iterations and contributes O(3) operations, which is constant. Then, the second inner loop also iterates over the 3 lanes, but for each lane, it checks all other lanes to update the minimum sideways jumps. This involves 3 iterations for the outer lanes and another 3 iterations for the inner lanes, resulting in a total of 9 constant operations. Together, these two loops contribute O(3 plus 9, which simplifies to O(12). Since 12 is a constant, these operations are considered O(1) for each position. Finally, at the end of the track, the algorithm computes the minimum of the DP array, which is of size 3. This is an additional O(3) operation, or O(1). Overall, the inner operations are constant for each position on the track. Now, combining all the steps, the outer loop runs n times, and the inner operations are O(1) for each position. This results in a total time complexity of O(n) multiplied by O(1), which simplifies to O(n). Next, we analyze the space complexity. The memory usage is primarily determined by the dynamic programming array DP, which has a size of 3. This array represents the minimum jumps required to reach each lane at the current position and remains constant throughout the algorithm, contributing O(3) or O(1). Additionally, the algorithm uses a few auxiliary variables such as n and I, as well as another constant size array called next_dp, which is also of size 3. These auxiliary variables contribute an additional O(3) or O(1). Since no other data structures are used, the total space complexity becomes O(3) plus O(3), which simplifies to O(6). However, since O(6) is constant, the overall space complexity is O(1). To put this into perspective, let's compare the current optimized approach with a brute force or naive approach. In a brute force method, the algorithm would explore all possible sequences of lane changes. This grows exponentially with the number of positions n, resulting in a time complexity of O(3 to the power of n. This is because there are 3 possible lane choices at each of the n positions. In contrast, the current solution leverages dynamic programming to avoid redundant computations. By storing the minimum jumps required for each lane at each position, the time complexity reduces dramatically from O(3 to the power of n to O(n), and the space complexity reduces from exponential space to constant space, or O(1). Considering the best, worst, and average cases, the algorithm consistently performs O(n) operations. In the best case, where there are no obstacles, the frog traverses the middle lane with no sideways jumps, requiring O(n) time. In the worst case, frequent lane changes are needed, but the algorithm still evaluates all lanes with a constant number of operations per position, resulting in O(n) time. Similarly, for average cases with randomly distributed obstacles, the time complexity remains O(n). Finally, let's summarize the mathematical proof of the big O complexities. For time complexity, the outer loop runs n times, and for each iteration, the inner operations are constant. This gives us O(n) multiplied by O(1), which simplifies to O(n). For space complexity, the algorithm uses only constant-sized arrays, such as the DP array and the next_dp array, both of size 3. These arrays contribute O(3 plus O(3 or O(6), which simplifies to O(1). Therefore, the overall solution has a time complexity of O(n) and a space complexity of O(1), making it highly efficient both in computation and memory usage. When solving this problem, it's important to be aware of common mistakes that can lead to incorrect solutions. One frequent issue is not accounting for lane-specific obstacles. If an obstacle blocks all forward movements in your current lane, you must ensure that you check other lanes for a valid path. Failing to do so can result in infinite loops, especially in recursive solutions. Another mistake involves the improper initialization of dynamic programming states. For example, the starting lane should have 0 jumps, while other lanes should begin with infinity to reflect their initial inaccessibility. This initialization is critical for propagating the correct minimum jumps as you progress. Hard-coding lane transitions is another pitfall. If you always jump to a specific lane, such as lane 2, you might miss edge cases where a different lane would be optimal due to obstacle density. Finally, ignoring edge cases, like when the road is obstacle-free or when obstacles are sparsely distributed, can lead to errors during execution. Robust handling of these scenarios is key to creating a reliable solution. Another mistake to avoid is using plain recursion without memoization. While recursion can be conceptually simple, its exponential time complexity becomes infeasible for larger inputs, such as when the obstacle array has a length of 10 to the power of 5. Memoization enables you to reuse previously computed results, drastically improving efficiency. From an interview perspective, this problem is a great opportunity to showcase your understanding of optimization. At its core, you're managing transitions between lanes while minimizing jumps, making it a classic dynamic programming scenario with overlapping subproblems. You can visualize it as a graph traversal problem, where lanes act as nodes, obstacles impose constraints, and jumps represent edge weights. Be prepared to explain why a greedy approach falls short, it doesn't account for future obstacles, and why dynamic programming is the optimal choice. Clear communication is key. Define your DP states, such as DP, I, J, representing the minimum jumps to reach position I in lane J, and explain how the transitions in base cases are derived. This problem shares similarities with several other LeetCode challenges, making it a useful foundation for related problems. For instance, in LeetCode 45, Jump Game 2, you also aim to minimize jumps, but without the added complexity of lanes. LeetCode 1696, Jump Game 6, is a more advanced version that incorporates a sliding window to optimize jumps under specific constraints. In LeetCode 1345, Jump Game 4, the focus shifts to graph traversal, minimizing jumps to reach the end. Lastly, LeetCode 935, Night Dialer, is another dynamic programming problem that revolves around state transitions, albeit in a different context. When considering alternative approaches, brute force is the most straightforward. You can recursively explore all paths by evaluating every possible lane change. However, this method is highly inefficient, with exponential time complexity, making it impractical for larger inputs. A more refined approach is dynamic programming with memoization, where recursion is combined with cached results to avoid redundant calculations. This is intuitive for those comfortable with recursion but requires careful handling of transitions in base cases. An alternative to memoization is an iterative dynamic programming approach, where you construct a DP table from the ground up. By updating the minimum jumps for each position and lane iteratively, you eliminate the need for recursion. This method can be further optimized using a rolling array to reduce space complexity. While this approach avoids the pitfalls of recursion, its implementation can be more challenging, as it requires careful indexing and updates. Lastly, there's the greedy approach, which aims to minimize jumps by always selecting the lane with the fewest obstacles ahead. While it's computationally fast, it often fails to account for obstacles further down the path, making it unreliable for scenarios with complex constraints. This approach can be useful for quick approximations in time-sensitive situations, but it's not robust enough for all test cases. When choosing a strategy, it's important to balance between correctness, efficiency, and the specific constraints of the problem you're solving. Great job! We've successfully covered the minimum sideway jumps problem. Remember the importance of dynamic programming and state optimization for problems like this. Thank you for joining, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!